Hello folks, in this session we're going to work through a problem in one-dimensional kinematics or one-dimensional motion. And I'm going to take a slightly different approach. We're going to focus on solving this problem strictly with graphs of acceleration versus time, velocity versus time, and position versus time. So the problem setup is this. We have a model rocket. It's going to be launched from the ground straight upwards, and the motion is going to just be straight up and down. In the future, we'll talk about projectile motion when you launch something from the surface at an angle, but on this problem, we're going to focus on one-dimensional motion straight up and down. The rocket is launched from the surface with an acceleration of plus 20 meters per second squared. So it starts from rest, but it quickly accelerates due to the chemical reactions in the fuel part of the rocket. And so the rocket accelerates up for 3 seconds at 20 meters per second squared, and then the fuel runs out. And at that point, the rocket is in free fall. In this problem, we're going to ignore air resistance. And so once the fuel runs out of the rocket's acceleration will be the free fall value due to gravity. In this problem, because we're gonna do things graphically, to keep things simple, I'm gonna approximate gravity, the acceleration of gravity, to be negative 10 meters per second squared. The accurate value is something around negative 9.81 meters per second squared, but we'll just round it off to negative 10 so that we can do this problem graphically. Once the fuel runs out, the rocket's in free fall for 10 seconds, and then in this problem, a parachute is deployed, and the rocket coasts back down to the ground at a constant speed, uniform velocity. And we will make the assumption that the speed at which the rocket falls to the ground is the value of the speed right at the moment the parachute was deployed. Okay, so that's the problem setup, and we'll put the words of the problem in a comment attached to this video. And so, how do we go about doing this graphically? All right, a really good approximation, or I wouldn't say necessarily good. It's good in some cases. In this case, it's going to be a good approximation. We're going to assume the acceleration is piecewise constant, which means that over any given interval of time, the acceleration will have a constant value, and then it can, after different intervals of time, it can take on different values, but over a given interval of time, we'll assume the acceleration is constant. And that will be a good approximation for this problem. In real-world engineering, there are cases where that will not be a very good approximation. For example, if we were to include air resistance, then the acceleration would not be piecewise constant. But we'll go with that approximation for this problem. All right, so the first step is we were given the accelerations over our intervals. So here I have an acceleration versus time graph, and I've already got the values plus 20 meters per second and negative 10 meters per second squared. That's 20 meters per second squared. And so piecewise constant means over that interval of time, we're going to assume that acceleration is a constant value. So I'm going to come up to this graph, and I'm going to make a constant acceleration. A constant function is just a flat horizontal function. So here's for that first 3 seconds of time, our acceleration is that constant value. Okay? We're going to assume our rocket starts from rest at the ground, but then quickly gains speed on the way up. So on the velocity graph, we're going to assume we have starting at 0, right? So this is 0 meters per second. And the speed is going to increase due to the engine of the rocket. Now, when the acceleration is piecewise constant, remember that the velocity is going to be made up of piecewise linear functions, okay? And so here we have a constant acceleration, which is flat. We want a function down here whose slope is a constant value, 20 meters per second squared. So remember, the relationship between acceleration and velocity is that acceleration is the first derivative of the velocity with respect to time. So here we have a constant slope, a constant first derivative. We want the acceleration as the first derivative of the velocity. So we want a function that has a constant slope of 20 meters per second squared. So that's going to be a function like this. And now we need to know the value. What is the velocity at 3 seconds? All right, so there's two ways of going about doing that. First, we can invert this relationship and write that the change in velocity is equal to the integral of the acceleration over time. Remember that an integral is really just area under the curve. So the change in velocity is the area under the acceleration curve. So I come up to the acceleration graph and we compute the area under this curve. And so this is delta Vy is the area under the acceleration curve, 3 seconds times 20 meters per second squared. That gives us a change in velocity of 60 meters per second. Okay, so that means at 3 seconds, we start at 0, we have a change of plus 60, so that means we end up at plus 60 meters per second. Another way to think about that is when you look at acceleration as these funny units, a meter per second squared. What is a square second? Another way to really think about that is when we say the acceleration is 20 meters per second squared, I like to think of that as 20 meters per second. In other words, after every second, the velocity changes by plus 20 meters per second. All right, so the acceleration is the rate of change of velocity. If our acceleration is plus 20 meters per second, it means every second the velocity changes by plus 20 meters per second. So at 1 second, we'd be at 20 meters per second. At 2 seconds, we'd be at 40 meters per second. And at 3 seconds, we'd be at 60 meters per second. All right, so that's that first part of this graph. And now on the position curve, let's come down here. If your acceleration is piecewise constant, your velocity is piecewise linear, it means your position is going to be piecewise parabolic, okay? So, and remember the relationship between velocity and position is velocity is the first derivative of position with respect to time, okay? And so here our velocity is initially 0. So that means on our position curve, we have an initial slope of 0. So the initial slope is 0 meters per second. So right here we start off flat, right? So the slope of the position graph is the velocity. The velocity is initially 0, so it means we have initially a 0 slope. And as we can see, the velocity is increasing in time, or the speed is increasing in time. So we want a curve here whose slope is increasing in time. And so that's going to give us a curve that looks like that. Let me redo that little piece. All right, so there is, as you can see, the slope is changing. The slope is initially 0, and then I can draw little tangent lines. So you can see the slope of the position is changing. The slope of the position curve is changing. Initially, the slope is 0 meters per second. At this point in time, at 3 seconds, the slope right here is plus 60 meters per second. So that's the slope. So we have a changing slope on the position graph. All right, so that gets us to there. Well, how high is that? What's the height of that? We can invert this relationship around using calculus, and we get delta y is equal to the integral of Vy dt. And again, remember the integral just means area under the curve. So the change in position is the area under the velocity curve. So I come up to the velocity curve and I compute the area here. Right, and that's a little triangle. So this area under the curve, I'll come down here. That area under the curve is the change in position or the change in height. And so that's a triangle. And so we're going to do 1/2 base times height to get the area. And so we've got 3 times 60, that's 180. Take half of that. So that's a change in height of 90 meters. So that's this area is 90 meters. So that tells us that if we start at 0 height, we're going to end up at 90 meters. So that's how high the rocket is when the engine cuts out. Okay? And a good check is down here, if you look at the position curve, we start out at 0 velocity, so the slope here is 0. The slope is increasing, telling you that the velocity is becoming a bigger positive number. And we can see this is parabolic, and it's parabolic upwards, it's concave upwards. Concave upwards means a positive acceleration. We can double check that here, indeed, we have a positive acceleration, okay? So concave up, positive acceleration. All right, so that's just the first 3 seconds. Now let's move on to the next 10 seconds. We'll go back up to our acceleration graph. And so at this point, the rocket gets to some height, gets up to 90 meters. The engine's cut out, and our rocket's in free fall. So the acceleration jumps down to a value of negative 10 meters per second. Right there. And it's going to keep that value for 10 seconds. So here's 3. We go 3 seconds. I should have mentioned that each of these hash marks is 3 seconds. And so 10 more seconds will take us out to 13. So this is 6, 9, 10, 11, 12. So we're a little bit past that. So that's, let's say, right there. So again, we're going to assume the acceleration is a constant value at negative 10 meters per second squared. Again, think of that as negative 10 meters per second, right? The acceleration is the rate of change of velocity. So negative 10 meters per second squared is every second the velocity is going to change by negative 10 meters per second. All right, let's come to the velocity graph. Right, we have here we have a negative value of the acceleration. A negative value of the acceleration means the velocity has to have a negative slope. All right, so we're going to go over here and we're going to have a negative slope, and we want to know what value it's going to end up at. Again, we can come up to the acceleration graph, compute the area under the curve. And so this is below the axis, it's going to be a negative area. So this is 3 to 13, that's 10 seconds times 10. So we've got a change of this area right here, delta Vy, this area, is negative 100 meters per second. All right? So that's the area under this curve. It's negative area because it's below the axis. We have time of 10 seconds, 10 times negative 10, area of negative 100 meters per second. And so we start at plus 60. We have a change of negative 100. That means that at 13 seconds, we're going to be at a value of negative 40 meters per second. So we come down to our graph over here. I'm going to place a negative 40 meters per second here. And we're going to come to 13 seconds. And we're going to connect these with a straight line. Okay. And if I did that right, we'll see that this should cross right at 9 seconds. Okay. So again, the area under the acceleration curve gives you the change in velocity. We have a change of -100. 60 minus 100 takes us down to -40. The slope, you can see the slope here, right? Whenever you have free fall, the slope of the velocity curve is -10 meters per second squared. So that's our slope there. This point's a really interesting point where the velocity crosses the axis when the velocity gets to 0. What does that physically mean? So our rocket, after the engine cut out, it was going up at plus 60 meters per second squared. Once the engine cuts out, the rocket doesn't just immediately start to go down. It actually goes up but slows down, comes to a maximum height, and then starts its downward motion. So at the highest point in the motion, right, the rocket momentarily comes to rest. So once the engine cuts out, your velocity is slowly is becoming more negative. So you start at 60 meters per second upward. After another second, you're going 50 meters per second, still upwards, but slower. And so as time goes on, you go from 60 meters per second upward, 50 meters per second upward, 40 meters per second upward, and every second that velocity goes down by 10. And so if you're at 60, after 6 seconds, you'll be at 0, right? So 60, after 1 second, you're at 50, another second, 40. So after 6 seconds, we'll end up back at 0 velocity. So this point right here is a very special point. This is where at the highest point in the motion. Okay. And so at this point, you get to the highest point, and then you start to move back downwards. All right, so let's come down to our position curve and sketch this out. Remember, if acceleration is piecewise constant, velocity is piecewise linear, our position is going to be piecewise parabolic. Our acceleration is negative, so that means we're going to want the position curve is going to have a negative concavity. And so we're going to have a piece of a parabola that has negative concavity, and we want the maximum point to be at 9 seconds. So here's 6, here's 9. I'm going to come up here, and so we're going to have a parabola that's going to get 0 slope right there. Okay, so our initial slope is 60, and now it's decreasing. So it's going from 60, 50, 40, 30. The slope is changing, and right at 9 seconds, we have a slope of 0 meters per second, and that's our maximum height. And then it's going to move downwards, and so we're going to all the way up to 13 seconds. So that takes us right to there. Now the question is, what height are we at maximum height, and what height are we at when the parachute is deployed? All right. To get that, we come back to our velocity curve, and we compute the area under the curve, because the area under the velocity curve tells you the change in your position. So we can compute this area right here. Do hashways the other way. That area right there, this is a triangle. It has a base of 6 seconds, right? So a base of 6 seconds times 60 meters per second, that's 360. And when you do a triangle, you do half of that. So this area right here is plus 180 meters. So that's the area under the curve. So that means we went from 90 meters, and now we're going up 180 meters, right? And so that's going to take us up to 270 meters. So that's our maximum height of our rocket. And then on the way down, we want to know what height is it here. So we come over to our velocity curve, we compute the area under the curve. Here we've got a little bit of negative area. So our change in height is, the base here is 4 seconds, 9 to 13 is 4 seconds, right? And our height is negative 40, so 4 times negative 40 is negative 160, and it's a triangle, so we take half of that. So that takes us to negative 80 meters, right? So we go from 270 down down 80 meters. That takes us to a height of 190 meters. So at 13 seconds, the rocket is at a height of 190 meters. All right, the last interval of time, we don't know how much time that is. We're going to actually try to figure that out. But our rocket is now going to, the parachute deploys, and now our rocket is going to gently fall the rest of the way at constant speed. So when you're at constant speed in one-dimensional motion or constant velocity, that means our acceleration is 0. So coming up to our acceleration curve, it's going to be a flat line right at 0. And we don't know yet how long it's going to go out to. It's going to go out to some time, and when it hits the ground, and we'll figure that out. So if your acceleration is 0, that means your velocity is not changing in time. So we come over to our velocity graph, and so for the rest, I'm going to have to erase this right here. Our velocity is going to be a horizontal, flat, constant value stuck at negative 40 meters per second for the rest of the way out to some time we don't know yet. Okay? And on this graph, here we have a slope, right? So at the highest point, your slope is 0. When the parachute is deployed, our slope is negative 40 meters per second. And it's just going to stay that constant slope for the rest of the motion until it goes all the way back to 0 height when it hits the ground. So here we hit the ground. Okay. All right, so how do we figure out the time at which it hits the ground? Note that we're going from right when the parachute is deployed, we're at a height of 190 meters, and we're going to end up at 0 height. So our height in this interval of time from 13 seconds on, our height is going to change by negative 190 meters, which means the area under this curve over here from 13 on, this area has to be 190 meters. So that will tell us what time it is. We need to go out far enough, right? We need to go out far enough such that this area is negative 190, right? And so this is a rectangle. So we just going to do what base will give us an area of 190 with a height of that rectangle being 40. And so that's just going to be a time of 19 over 4, 190 over 40. So 19 over 4. All right. So we're going to need an additional 19 over 4 seconds. All right. And so that is actually equal to, if it was 20 over 4, that would be 5 seconds. So we're actually at 4.75 seconds additional time. So 4.75 seconds time, so that's our base here, times the height of the rectangle, gives us an area of negative 190, and that will take us from this point all the way back down to the ground. So that's how we figure out what this time is. It takes 4.75 seconds to hit the ground. And when it hits the ground, it's going to hit the ground that whole way down. Once the parachute is deployed, it's going to stay at that constant value of the velocity. So it slams into the ground at 40 meters per second. Now, that finishes this problem. You could have done it maybe slightly faster if you just dived into the equations, the one-dimensional constant acceleration equations. But I wanted to take this graphical approach because I wanted to make the connection with the graphs and the underlying calculus. Thank you.